Let's consider the probability of OR events. Okay, so for example, suppose we roll a single die. What is the probability of rolling either a 2 or a 3? All right, so these are considered to be non-overlapping events, meaning we couldn't get both of them at the same time. All right, so that's because we're rolling a single die. That does change if we roll 2 dice. But for just a single die, it's either a 2 or a 3, but we don't have to worry about it being both of those two things. All right, so the rule for finding the probability of non-overlapping events when you're dealing with an either-or situation is to add the two probabilities together. Okay, because we're interested in an event which has a greater number of outcomes, so we just have a larger probability, or the two chances added together. Okay, so what is the probability of rolling a 2? Right, and what is the probability of rolling a 3? And then we'll add those together. All right, so the probability of getting a 2 is 1 out of 6. Probability of getting a 3 is also 1 out of 6. And then together that's a probability of 2/6 or 1/3. Now this one's simple enough. If you were to list out the 6 outcomes, I think you could easily see that 2 of them satisfy this property of being either a 2 or a 3. So you would I think know just by counting that it's 2/6. So it helps to do some simple examples like this just to build your intuition, and then you can start using these rules in situations where you have a really large number of outcomes, and maybe it's not as easy to make your list to verify that this is correct. Let's consider the probability of an overlapping event. So let's say we wanted to now ask, what is the probability of getting either a queen or a club? All right, when you draw a card from a deck. All right, so if we were to just add the two probabilities, right, there are 4 queens in a deck, so we have 4 out of 52, and then there are 13 clubs, right, and if you add those, you would think that the probability is 17 out of 52, right, but if you actually just count up all of the different cards in the deck that are queens or clubs, you're going to see that there are 16. And of course, the reason for that is that one card was double counted. We have the queen of clubs, which got counted as part of the queens and counted as part of the clubs. All right, so the strategy for counting, for finding probability with overlapping events is to start with the 2 individual probabilities, and you add those together, and then you have to subtract the probability of both of those things, okay, or of getting, for in this example, a queen and a club. All right, and we know that the probability of that would be 1 out of 52. All right, and then this can be generalized. It doesn't have to be just 2 events, but this is how you would do it with 2 events. All right, so the subtraction is just to get rid of the overcounting. All right, here's an example. There are 8 women in a room, 2 Democratic men, 2 Republican men, 2 Democratic women, and 2 Republican women. If you select one person at random from this room, what is the probability that you will select either a woman or a Democrat? All right, so what we want to do is find the probability of selecting a woman, the probability of selecting a Democrat, and add those, and then subtract the probability of choosing a person who is both a woman and a Democrat. All right, so the probability of choosing a woman, well, we have 2 Democratic women and 2 Republican women, and there are 8 people total. All right, so 4 out of 8. The probability of choosing a Democrat, we have 2 Democratic men and 2 Democratic women, so that's also 4 out of 8. Right, but out of those, if we just added this, notice this is a good clue that something's not quite right. If you just stop there, you would get a probability of 8 out of 8, which is 1, which means that it's absolutely certain that you would get a Democratic woman when you choose a person at random. And of course, we know that's not the case because there are some other options. All right, so that means that we must have double counted some people in these tallies of 4. All right, so then how many people are both women and Democrats? Well, we know that that's 2. All right, or 2 out of 8. All right, so then the probability now is 6/8, which is 3 out of 4. Now, if you're interested, we can extend this. So let's say we're dealing with three events, A, B, and C, and let's say we want to find the probability of A or B or C. This is where it gets interesting. All right, so if we were to, let's call these three circles A, B, and C, and let me shade these in to represent adding these probabilities together. All right, so if I count, let me color code these. Okay, so if I add the probabilities together, I'll represent that by coloring. So let me color one circle to represent the probability of A. Okay, and then to count the probability of B, I would be counting here. We'll call that the circle that represents B. And then the probability of C, I'll call this circle down here. Okay, so we've done probability of A plus probability of B plus the probability of C. Okay, so now the question is, how many times have we overcounted? All right, so look at where the shading of the circles overlaps, and that indicates double counting as we added these things, just like with the queen and the clubs. All right, so I have a few regions right here and here and here that were each double counted. All right, so everywhere, like where A and B alone overlap, you can see that that region's shaded purple and blue. I've got a blue and orange, and I've got a purple and orange. And then the little region in the middle has actually been colored 3 times, blue, purple, and orange. So that was triple counted, right? So to get rid of the extra counting, I'm going to go through and subtract the things that were colored twice. All right, so I want to subtract the probability of A and B, right? And that's going to be this little region right here. Whoops. Okay, where A and B overlap, right? So that's going to take away, by subtracting, I'm going to take away one of those colors. So for example, I might be taking away the purple, right? And then that would leave this spot colored just blue, and this spot would still be double counted. It would be blue and orange. Okay, and then I will also subtract the probability of B and C, right? And that's going to get rid of some coloring between purple and orange. Okay, and then I want to subtract the probability of A and C. Right, and then that would erase the coloring here. All right, so now I've erased the coloring here, here, and here. Okay, so but only one of the colors. So I've taken like maybe the blue away here, maybe the purple away here, and maybe the orange away here. All right, so these regions are all counted just once. We fixed that, but now I've done 3 subtractions. So if you look at the middle section now, right, that actually is blank. It's not colored at all, right? So this is what it looks like now, right? But if I want to find the probability of A or B or C, I still do want to count something that is all 3 of those things, all right? So I need to add that probability back in to make sure that I do count it, right? So I've got all of this stuff, 3 probabilities added, 3 subtracted, and then I want to add back in the probability of A and B and C. Okay? Now you can extend this as much as you want. So what if we want the probability of 4 overlapping events? And this is not as easy to draw with a Venn diagram, but I can still use that same process, right? So what I would do is I would add together the probabilities of the 4 events, and then I would start subtracting the things that were overcounted, right? So I would subtract the probability of A and B, and the probability of A and C, and the probability of A and D, right? So all the pairs of 2 things, and the probability of B and C, B and D, and C and D, and then I need to add back in the probability of the intersections of three things, so A and B and C, and A and B and D, and B and C and D, and A and C and D. All right, and then finally subtract the probability of all four, A and B and C and D. Okay, so that's a lot, but if you're interested, that's how you would do it. And if you were to extend this to 5 things, then you would just add up the probabilities of all 5, subtract the probabilities of pairs of 2, add the probabilities of groups of 3, subtract the probability of groups of 4, and then finally add the probability of groups of 5. All right, let's talk about the probability of events that involve the phrase at least once. All right, so if let's say we're flipping a coin 10 times and we want to know what's the probability that we'll get tails at least once, then there is a rule for this. Okay, so let's suppose that the probability of an event A occurring in one of those trials, so for example flipping one coin, is probability of A. If all trials are independent, so this rule does require that, then the probability that that event, so for example getting tails, occurs at least once in n trials, however many times we flip the coin for example, then the probability of getting at least one event A is 1 minus the probability of getting no event A in n trials. All right, so we've seen that probabilities like this, where it must be one or the other, add up to 1. All right, so either we get a tails in one of our trials or we don't get tails in any of our trials. All right, so we can just subtract that away. And then here's the claim. This equals 1 minus the probability of not A to the nth power. All right, so let's do an example. Let's say we toss a coin 3 times. We'll keep the numbers smaller. All right, and we want to know what's the probability of getting tails at least once. Okay, so here's our formula. You would subtract away the probability of not getting tails in any of those 3 trials. All right, well, what is the probability of not getting tails? All right, well, that would mean if we're not getting it at all, even once, that would mean that it's always heads. All right, so when the first time we toss the coin, the probability of getting heads is 1/2, and then the probability of getting heads the second toss is also 1/2, and then it's also the same the third time. All right, so that probability of not getting tails or getting heads is going to be the same no matter how many times we repeat this trial, because these events are independent. All right, so that part is important. And then we can just summarize, instead of multiplying 1/2 3 times, we can just say that that's 1/2 to the third. All right, or in other words, there's a 1 in 8 chance that we wouldn't get any tails at all, that they would all be heads. And if you think about this, when we've drawn out the options before, I think we've even done this one. So if you list out heads, 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 tails, heads, tails, tails, heads, and so forth, all of those options for 3 coins, there's going to be 8 different outcomes, and only one of them is going to have all 3 heads. All right, and then to finish this off, the probability of getting at least one tail would be 1 minus 1/8, which is 7/8, and that agrees with what we've seen before as well. All right, now if you are dealing with dependent events, you can use a modification of this formula. You would just need to play around with this probability of not getting A in n trials. All right, so it wouldn't necessarily be the same number to an exponent. Your number might change in that case, but you could still use this 1 minus idea from this formula. All right, let's try one more example. Use the at least once rule to find the probability of getting at least one head when you toss 3 coins. I think I jumped ahead of myself with the last example here, so this one's too similar. Let's do a different example. So we'll just make something up. let's say we're going to roll a die 8 times, and let's try to find the probability that we get a 7 at least once. Okay, so we would, the probability of this would equal 1 minus the probability of getting no 7s in our 8 rolls, okay, which would be 1 minus the probability of not getting a 7 in 1 roll, right, and then that raised to the 8th power since we're rolling the die 8 times. All right, so what is the probability of not getting a 7? Well, when you roll a die once, there are actually no ways to get a 7. I think I was thinking sums here. My video software doesn't let me edit this, so you're going to just have to hear my mistake here. But let's change this. So what's the probability of getting, let's pick a number that actually is on the die. So let's go with a 5 instead of a 7. Let me change this. Okay. All right, so what is the chance of not getting a 5 when you roll the die once? All right, well, there are 6 total outcomes, and 5 of them are not a 5, so that would be a 5 out of 6 chance, and then that to the 8th power. And you can use a calculator to find this. This is about 0.7674, right? Or we could say about 76.7% chance. All right, so that's it for finding the probability of events involving at least once. We will return to this again in a few sections. If you read the chapter opener, we looked at the birthday problem, right? What are the chances of finding 2 people with the same birthday, right? So we can use this rule. We just need one more thing in order to be able to apply this. But remember this, we'll come back to it.